Hi everyone, EasyPeps here. Welcome to another Houdini tutorial. In this video, similarly to my previous one, we are going to use a SopSolver and some VEX code to generate geometry. And for this one, the idea is to have some points to start the animation that will move toward a certain direction. And eventually we want this point to be able to change their direction and also maybe to split. And finally, we want to generate some shape on the intersection of these points. So let's start from a Houdini empty scene. Let's drop down a geometry and let's call it lines and dive inside. In here, we want to drop down a attribute Brangle and we want this set to details because we don't want to reiterate this code on some geometry. We just want to generate the starting point once. In here, let's first create an integer variable that we will bind it to a channel. We will call this points and we will create these pair parameters. So with this one, we will choose the amount of point to start the animation. And let's just keep it at 1 for now. And somebody pointed out in the last tutorial the code wasn't really visible, so I will press Ctrl+ to zoom it a little bit. Hopefully it will be enough, otherwise in the next tutorial maybe I will use some external editor. Now we want all our starting code to run for each point we define here. So let's create a for loop, and for I is equal to 0, I less than our number of points, and I++, so we'll increment by 1 for each step. Let's close the loop. And also I want to rename this to starting points. Now in the loop, before taking care of the moving point, we know that we want to create some lines. So we need points that will stay still on the origin to create the starting connection. Also, let's drop down a comment so it will be more clear to read. So origin points. Let's see, we want to add some points, so let's create an integer variable. We will call this orig and we will use the add point function. So first geometry index on the current position. So now we are running this loop only one and we have 1 point on the origin. Now for the moving points, let's also drop down another comment, and we want to create another point. We will call this pt. We will use the point function again on the current position, and we want to assign some initial velocity to this point. So let's create a vector variable. We will call it v, and for now we just set it on the z-axis. Now we need to bind the variable to the point attribute, so set point attribute function. First geometry index, we want to bind it to the v attribute, to the point we just created, using the v variable we just created, and using the mode set. So now we should have a velocity attribute. Yes, click it to create the visualizer. And if you recall my last video, inside the solver we will use a code that will run only on a defined group. So already set point group function we will use on the first geometry index. We will create a group that is called grow. For the current pt, it will be add to the group, so 1, and the mode will be set. So now we should also have a group with 1 point, because we didn't set it on the origin point, and it's good as it is. So now let's drop down a solver, plug to the first input, and dive inside. In here we want to drop down a point Brangle. This time we want the code to run on our points, and we want to run it only on our growing group. So let's bind the group to grow. And right off the bat, we want to create some channel that will allow us to control the whole simulation. So let's create a step variable. We will create an integer channel. Let's call it step. And then we want to create 3 float variable, one for the speed, one for the rotation possibility to happen, and one for the splitting chance to happen. So for the speed, we will create a float channel we will call speed, and same for the other two. So rotation, let's say rot chance, and split chance. Let's create the spare parameter, and here we have it. So now on our moving point, we want to add the velocity we created before on our current position. So plus or equal v at v, and we want to multiply it by the speed channel, so we will be able to control the speed of the movement. And let's spin this parameter and go outside to see the solver work. Let's set the speed to 0.1. Turn on the real time, and as you can see, the solver is working. We have a moving point on the vector direction we assigned. Now, for the step channel, I actually ended up not using it in my final animation, but I believe it's a pretty convenient way if you want to add some step effect to the whole thing. All it takes, we just need a condition with an if, and we want to check if the current frame, or to be more precise, if the modulus operation between the current frame and the step channel will be equal to 0. So when this value will be equal to 0, all our code will run, otherwise it won't. So if we set this step to 10 and play the animation, you can see that the points move every 10 frames. And this happened because the modulus operation, basically it returns 0 when this division will have no remainder, otherwise it will return 1. Meaning that on frame 10, this will be 0 and our point will move, and so on every other frame that will be divisible by 0 with no remainder. Otherwise, our point will not move. And in my final animation, I just set this to 1, so it will run on every frame. And if we drop down an add node after the solver, let's unpin this parameter. Here we want to go on the polygon tab and say by group. So now we do have a growing line. But if we increase the number of points and let the solver resimulate, all the lines are going the same direction because we hard-coded the velocity. So we need a way to randomize this velocity value. The thing is, for the logic of the direction change we will do later on, we will apply a rotation. This means we need a velocity vector, and we also need an up vector that needs to be different from the velocity one. Using just random function, we have the risk to end up with the same value for the velocity and the up vector if we don't include some other check or condition. So we will do it with another approach, and let me just put the display flag here. So we want to create a list with all the possible direction our point can take, meaning they can go on the X, Y, or Z direction, both positive or negative. But for the list, we just need the positive direction because we can use another value to flip it on a random chance. So let's create our list. We will create a vector list. We will call it dir list, and we will say that it's an array with the square bracket. It will be equal to, we said, 3 directions, so 1, 2, and 3. And the first one will be on the X, so 1, 0, 0. The second one on the Y, 0, 1, 0. And the third one will be 0, 0, 1 on the Z-axis, semicolon. Now we do have our list. You can check it if we bind it to a vector attribute. Dir list is equal to dir list. You can see that on the details we have the list with our possible direction, at least the positive one. So now we want our points to take one of this direction. And also let me just quickly add our I variable on the X position. So just to visualize this, the point won't overlap with each other. So we need a random index for each point that will go from 0 to 2 because we have 3 values. So let's create an integer variable. We will call this dir_index. And let's see, we want to have a random value and we can use the I variable. So now we do have a random value. It goes from 0 to 1, but it's a float value. And we said we need a value from 0 to 2 only with the integer 1. So first we want to fit this value from 0 to 1 to 0 to 2. And then we want to float it. So we will end up only with the integer value. The problem is now with the floor value, we are taking the smaller integer. So this max of 2 won't work. We need to set it to 3. Now, as before, let's bind it to an integer attribute this time so we can visualize it. dir_index. And there it is. Of course, we are just seeing 1 because it's running on the details, but it's just for visualization. We can also delete these two because they are working. And now for our velocity, we want to take from the dir list with the dir_index of the points. As you can see, is working. Of course, it's taking only the positive values for now. And to fix that, we just need to multiply this direction by a variable that we will call it reverse. And this value could be either 1, so the direction will stay the same, or -1, so the direction will be flipped, based on a random chance. So let's create this variable, reverse. And again, we will use the I variable, but we want to multiply it by a different number, so we basically introduce a new seed. So now we have our value between 0 and 1, and it's also a float value. This time we will use the int function on it. So now we have an integer variable, and it's either 0 or 1. So now the idea is that I'll just borrow Houdini workspace so I can draw on it. So now we have either 0 or 1 as an outcome value. And since we know that every number elevated to 0 is 1, if we take -1 as a base number, we can end up either with 1 or -1. So all of this is our exponent, and the power function, you put first the base number, then comma, and the exponent. And by default, the power function returns a float number, so we just explicit cast this into an int. And now we have both positive and negative direction. So now that we have our velocity, we can create the other vector, the up one. So let's start from the end of the workflow. First, we want to create an attribute. We will call it up, and we will assign the up variable that we are going to create right now. So vector up. We want to basically take another direction from the list, but we said that this direction needs to be different from the velocity one. So before assigning the direction to the up, we want to remove the direction we just took with our velocity from that list. We can do it with the remove index function. We say from which list, from the dir list, and we want to remove the dir index. Now for the up variable, we can say take another direction from the list, and this time, since the rotation could happen on either of the remaining direction, we can just use the first index, because they will both work. And now, if we create an attribute visualizer for the up vector, and also go here and change the color. You can see that we have two vectors, one for the velocity and one for the up vector, and they're all different. So now if we go here and play the animation, we have the points moving in different direction. Of course, we still don't have any direction change or branching, so it's quite boring. And now let's delete this addition here to the position. That was just for visualization. We want the points to start only from the origin. And of course, if you change this number, you can even bind it to a channel. We change the seed for the whole thing. So that's it for the starting point. For now, let's set it to 1. And we want to go inside the solver, pin the wrangle parameter and go outside. So we can edit it, but have a visual feedback without going back and forth. Now in here, let's write a comment so we will know that from now on we are handling our direction. And the idea is that we don't want this rotation to change, this direction to change on each frame, so we want to establish another condition where we will compare a random value that will change on each frame and our rotation chains. The value we're going to generate will be from 0 to 1, so if we put our rotation chains to 0.5, this condition will be triggered half of the time. So here we want to create a variable that will hold our direction seed. Let's call it dirseed, and we will set it 0 for now. And our condition will be if our dirseed will be less than our rotation chance that we called R chance, then our direction will change. Otherwise, the point will keep going. Now, for the direction seed, we want a random number, and we can sample it from the point number, and plus a new float channel. We will call it dirseed, so we can change our seed without hard coding it. I miss a parenthesis. Let's create this pair parameter. And we want this number to change over time, so we also want to include the frame in the seed and multiply it by the point number. So if we say inside the condition set the color to red, you can see that, let's disable the visualizer, the point will flicker. We also need to say here, let's set it to white, C111. Now the point should flicker half of the time. Yes. So we know that it's working. So let's delete this one and also this one. And we want to re-enable the visualizer, and let me do a screen. Now, when our condition is met, if we generate our new direction with some random function, or at least like before, we could end up with two possible outcomes that we want to exclude, because we could have the previous direction as the new one, or the opposite one, so the point will come back on the line, and we don't want that. So the idea is that instead of generating a new velocity, we will apply a set of rotation using the vectors we just created. So what we're going to do is to create first another vector that will be this one. Then we're going to rotate our velocity on this vector by minus 90 degrees. So it will go over there and it will match our up vector. And then we're going to rotate it another time on the old velocity, and the second time we want to rotate it either by 90 degrees, 180, 270 or 360. So we can end up with any of these outcome. So first let's create the red vector which was going into the z-axis, and that vector can be calculated with the cross product between our velocity and our up. So let's create a vector variable, we will call it cross, and it will be equal to the cross product between our up vector and our velocity. and semicolon. So now if we bind it to an attribute, it's equal to cross, and create a visualizer, cross, make it vector, what is it? Oh, marker and vector, and make it red. Now we do have our vector to make our rotation. So now we need the angle. So let's create also a float variable for the angle. Let's call it angle1 because we need to do a second rotation. So this will be the first. And let's create a float channel. We will call it angle1. Create this pair parameter. And we want this to be, we say negative 90. So edit parameter interface. And let's make it from negative 19 to 0. Apply and accept. And also this angle needs to be expressed in radians for the rotation we're going to do. So let's do radians function. This will convert the angle from degrees to radians. Oh, and also indent here, otherwise it will never work. Apply and accept. Now what we want to do is want to use quaternions to apply this rotation. Now, without going too deep into quaternions, let's just say quaternions are a convenient way to express and apply rotation. In the specific, we're going to use this function that says rotates a vector by a quaternion. For the first rotation, we want to rotate our velocity. And if you click on quaternion, you can see that quaternions can be expressed in many ways, and this one requires an angle and an axis. And this is precisely what we have. So we can say with that qrotate function to rotate this velocity vector on a quaternion that we're going to create with the negative 90 angle and this axis, the red one. So first let's create this quaternion. And let's close this. Over here, after the cross product, let's create a vector4, which is the type of data needs a quaternion. And we will call this quat1 because we will need two of those. And it will be equal to quaternion. The angle is angle1 and the axis is cross. So now we can use the qrotate function to rotate our axis on this quaternion. Our axis again is the velocity in this case. And we want to store this new vector inside a new variable. Let's call it rot1. So now let's bind it to visualize it to an attribute and create the visualizer, rot1, set it to vector. So marker, vector, and make this, let's say, light blue. So now it's matching our velocity because the angle is set to 0. As we decrease the angle, you can see that it's going to match the up vector because it's rotating on the cross vector we created. And that's it for the first rotation. Now we need a second rotation. To apply either 90, 180, 270 or 360 degree rotation to this new vector we created. So first let's create this, let's call it random angle. And you can actually create it in multiple way, I guess. I will just create a list with all the possible angle. So it will be a float angle list. It will be an array. And it will be equal to 4 values, so 90, 180, 270, and 360. Then I want to create a random index because I want the point to choose randomly from one of each of this angle. So let's create an integer variable. Let's call it angle2index. And it will be random, and we can sample it from the point number. So now it's a float value from 0 to 1. We want to fit it from 0 to 1 to 0 to 3, which is the maximum index of our array, semicolon, and I don't need this parenthesis. Now we have a warning because this is a float value, so we can floor it like before. And since, again, the floor takes the smallest integer, we need to step up the maximum value by one integer. So now we do have the current index, and we can say, let's make some space. Here we will create the angle 2. It will be equal to a random value from the angle list, and the random value will be picked with this angle 2 index we just created. And we wrote the angles in degrees, so again we want to convert this to radians. So now we can create our second quaternion, so vector for quat2, and this time the angle is angle 2, and the pivot of the rotation is the old velocity vector, so v at v. And also specify here v at v is just in case. Sometimes it's needed to specify the attribute time, like if you do a custom attribute, in case of the position or the normal, and I believe even the up one, since they are like hard-coded in Houdini, you don't have to specify the type before. So now let's create our funnel vector. We will call it rot2, and the qrotate function this time will take the quaternion 2, and the vector we want to rotate is the blue one. We called it rot1. Create a visualizer. Let's quickly copy this one. So 2 and 2. Where is it? Rot2. Make it vector. Let's make it purple. As you can see now, as rotated in this direction, and where is the? Let's add a float channel. Let's call it rot seed on this one, so we can control and check. Yeah, it's working. As you can see, either 0 or 360, 90, 180, and 270. Now we do have our final vector, but we can just update the velocity of the current point. Otherwise, the point will continue moving and we won't have geometry to create the line. So what we're going to do is to stop the current point, we create a new one, and we will assign the new velocity to the new point. So after we created the quaternion, let's create a new integer value. We will call it npt, and add a point with the add function to the current position. So now after the rotation, we can set the point attribute. For geometry index, the attribute will be called v on the npt we just created, and the vector is rotation 2, which is our final rotation. Let's write the mode to set. And now at the end of the condition, we want to use the, let's write a comment and let's say update group, because now we have to set the new point to the grow group and we need to take out the old point from the grow group. So set point group, geometry 0, the group was called grow, and we need to put npt in the group, so 1, and set, and copy and paste, and this one is 0 and the on the current point number, so at ptnum. So now let's test it. Turn off the visualizer, and as you can see, it seems it works, but then it stopped working. And that's because the new point we created doesn't have the up vector anymore. So after we create the point, the new point here, we want to, let's copy this line. We want to assign the up vector using our old velocity. So it will have a new vector to perform the rotation. So let's quickly test it. And as you can see, now it's working until a certain point. And this is not a problem of the code itself. This is a matter of precision, meaning that by default, the wrangle node can't handle the accuracy required by this calculation. And to solve this, we want to go inside the solver, and on the wrangle that is handling the code, we want to go to bindings and set the vex precision to 64-bit. Now, if we redo it, you can see that there is not more collapsing due to lack of data. So go back on the code. Basically the core functionality of our workflow is this one. The point is currently moving, updating its direction, and we can control the rotation change. If we set it to, let's say, 0.9, the rotation will happen very frequently. If we set it to 0.1, it will happen very rarely. And also we can control the speed. Let's set it back to 0.5. We can increase the speed of this whole thing. And also we have that stepping thing. And I believe that's pretty cool. Also we can change the seed for the rotation and also the direction here. Now we want to take care of the splitting of these points. But before doing that, we need to take care of another problem, because if we now increase the number of starting points, let's set it to 6, you can see that the add node will mess things up. And this is because we are creating more points, so the add node doesn't know how to connect because they are not in a proper order. To fix this, we want to create a name attribute for each line. So we can change here to by attribute and use that attribute to drive it. So first, let's go on the starting points, and here inside the loop, let's create a new string variable. We will call it name. So string name. This will be equal to line, and we want this attribute to be different for each line. So we want to add the I variable to this one, so plus I, and it will give us an error because we are adding an integer to a string. So let's convert this I to a string, and also copy this line so we can bind it to an attribute. So set point attribute 0, the attribute will be called name, and the point is this origin we are creating, and also the value will be name. And now if you go on the geometry spreadsheet, you can see that the origin points does have this new attribute. And now we want to assign this name also to the moving points. So after the up, and this will be, how we call this, PT. So now also the other one are inheriting the name. And of course this won't be enough, even if we specify the name attribute, because we still need to transfer that attribute to the new points we are generating. So let's copy this set point attribute line, and inside the solver, at the end, after we assign the velocity, we also want to assign this name attribute to the MPT. This is the new moving point, and we don't have the variable name, so this time we want to take it from the attribute that is coming from the geometry. So now hopefully it should work. Yes. So now onto the splitting part. Now for the splitting, we want to, let's also, like before, pin this one and delete all the attribute we created for visualization. We want the splitting to happen only when the direction change is happening. So all of the splitting code will be inside the previous condition, and we can do it before updating the group. So let's write a comment, split And here will be basically about reiterating what we did so far on a second point. So just like before, let's copy this old condition. We will change a few things. So this will be called split seed, and also rename this channel. Frame and ptnum are fine. And here the condition will be if the split seed will be less than not the R chance, which was for the rotation, but this other one, which was S chance. So S chance. So if this is true, the splitting will happen, otherwise it won't. Oh, and by the way, if you're already seeing some splitting, it's not actually splitting. And this was the reason because I ended up with only one starting point. So I want to set this, let me unpin. Basically, we don't have enough direction to be all the point on different paths. So eventually you will notice something like a splitting, but this is actually more than one line that eventually will change the direction in this point. So I want to set this to 1, and now there is absolutely no splitting yet. So basically, when our condition is triggered, let's say on this point, we need to create a new point that will move in one of the remaining direction, one of the remaining angle that we use on this one, on the second rotation. So first we want to create a new point. Let's call it spt, add point function, 0 geometry on the current position. And we also need another point because we always need the, let's say, the root to connect the outgoing lines. So let's also create another point. Let's call it OSPT for origin split point, and same as always, 0 and at P. So let's make some room. And like before, we need to transfer the up vector to the new point that needs to move, otherwise it won't have a vector to do the rotation. And now, just like for the previous point, we want to do the rotation operation. So this was the rotation, so after this, let's make some room. This will be our rotation 3. And in this case, we just need one, because the first rotation we can take this one, it was the same. It will alienate the normal to the up vector, the velocity to the up vector, sorry. And this time we need to rotate it over a new quaternion, because we need a different rotation from the other point. So we are going to create another quaternion, so vector for quat3, and it's quaternion, and we will need a third angle, and the vector for the second rotation is the velocity, and of course we need to create the angle, and the angle needs to be picked from the angle list we created before. So let's take the line where we declare the angle 2. Let's copy it here, and this will be angle 3. And we need a new index, so let's also copy the index line, which was this one. And let's paste it here. This is angle 3 index. And let's see, fit, run, and we will call a new channel. Let's call it split seed. Create the spare parameter. Oh, we already added the split seed. Split seed, split angle seed. All right. Now the problem is I don't want the same angle of the other point to be chosen. So before assigning the angle from the angle list, we want to remove the angle the other point has chosen from the list. So remove index from angle list, we want to take out the where it is, angle to index. And also we want to change this 4 to 3 because our list has one element less now. So now let's copy the line for the velocity and paste it after the rotation. Here we are assigning the velocity to the SPT, and the rotation is the rotation tree we just created. And also we want to copy the line for the grouping because we want to set also the SPT to the grow group. So here SPT1. And now the point should be fine, but we should have problem with the connecting lines. And also we need to set some split chance, let's say 0.2. Yeah, the line are splitting, and now we want to fix this connecting issue, and we just need to fix the name attribute. So basically every new split has to have a new name. So after we created the point, we want to create a new string variable. It will be our branch name, let's call it like that. And it will be equal at the current name, and we will add it branch plus the current SPT number converted to string, so we can have different name from each other. And now here we want to set it as a new name attribute for the current point. So name for SPT, the value will be branch name. And we want to do it also for the origin SPT. So let's copy and paste and add an O. So let's see. Yeah, now something is working and something is not working. Let's see what we did wrong. Split. Oh yeah, this one has to be assigned to the SPT. We didn't update the value. Yeah, so now it's working perfectly. Don't go too crazy on this, especially if you set up a height split chance. Let's set it to 0.1 because this is a recursive thing, so the points will increase exponentially at a certain point and it will become slow over time. But during my test until let's say frame 300 it was perfectly fine. And that basically concludes the lines part. So let's drop down a null after the add node. We will call this out lines, and before that we want to use an attribute delete so we can clean things up. We can basically delete everything here. The position will be never deleted even if you say anything. And also a group delete node. We don't need the grow group anymore. Now we want to generate some shapes when our conditions are met. And I want to generate a box where the point only change direction, and an octahedron where the point split with another point. So first we want to take care of the octahedron. It will be more easy because we already have the point to copy the octahedron on. Is the let me go back into the rectangle. Basically we want to copy an octahedron on this OSPT point. So after we created this OSPT point, we want to set another point attribute, and we will call this one copy on the OSPT, and we will give the value split because this will be the split geometry, and mode is set. So now let's see if we go forward and expect the geometry spreadsheet. You can see the sum of the points as the new split attribute, this new copy attribute, and this new point have the split value. So we can drop down a blast node, and after the solver before the adding, we are branching with a new node, and we can say that at copy is equal to split. So now if we delete non-selected, we only have specify points here. We only have the splitting points. So we have the points to copy the octahedron onto. So let's take a platonic solid, and this will be our first shape. We say the octahedron, but of course choose whatever you want. Copy to points node, and we want to copy this on this. And now let's drop down a merge node, another null. Let's call it out octa, and merge these two guys together. Of course they are too big. Now we are going to handle some p-scale. So let's drop down a point wrangle here, and we want to randomize the p-scale a little bit. So let's create a random variable. Let's call it rand, and it will be a random function over the point number, and we want to bind it to the p-scale, so it's equal to rand, and we want to fit it also. So let's fit 0,1 this value with two new channel, so min p-scale, max p-scale. I always forget one parenthesis, and let's say 0.4, 0.8, and let's say 0.05. We want to be very small. This is too much. Something like this. And we don't want this to appear like this suddenly without any kind of animation. So now we're going to create a counter to control the shape animation. So we want to go back inside the solver, and here on the OSPT, so the points for the octahedron, we want to create another attribute. Let's copy this line, and this attribute we will call it counter over the OSPT, and it will be an integer attribute, and we will initialize it as 0. So now the OSPT will also have this counter attribute. And now here at the end of our code, before the final parenthesis, we want to create another for loop. So first let's create a variable. We will call it npts, and we will use the endpoints function over the first geometry input. This variable will store the amount of points we have in our workflow. And now we want to create a for loop. So for int I is equal to 0, for I less the total points, so npts, and I++. And in this for loop, let's also close it. So first we want to do a check inside this loop. We want to check if the points has the counter attribute. So if as point attribute geometry 0, the attribute is called counter, we will do something, and this something is just to look for the counter attribute. So we will store it into a new variable. We will use the point function to retrieve the current counter, which now is 0, from the current point of the for loop, so I. Then semicolon, and now we want to increase that counter. So set point attribute geometry 0, the attribute is always counter. We want to set it over I, and we want to say counter +1, and the mode will be set. Oh, we need to close the loop, of course. So now if we go on the geometry spreadsheet, we should have a counter attribute on these points, and we don't have the points. Let me reset it. Okay. So we should have this counter that starts from 0 when the point is generated and then increase over time. Nice. So now we can use this counter attribute to multiply it with the p-scale. So let's see. Here we want to say e at counter by random. And of course now the counter is increasing forever, so we want to clamp this value. Let's say clamp from 0 to over 20 frame, let's say. So now at a certain point it will stop, and also let's do like this. It will be more clean. And let's decrease this value. Now, as you can see, it's a linear animation, so we can actually use a ramp to remap this animation. So let's create a ramp here. Let's say ch ramp. Oh, we already have the parentheses. And we will call it ramp scale, and all of this will be the seed for the ramp. Another parenthesis, no. Oh, we don't need this one. So let's create the ramp, and now if we convert it to B-spline, let's say we want to make something like this, like an ease in, ease out. If we put it on play, you can see that we have some easing. So now maybe decrease this one a little more, or even better, these two values. And let's copy this attribute delete. We shouldn't have the group. Yes, we do. We want to delete also the group. So we have some clean geometry. And maybe we want to add a little bevel on the shape. Let's say something like this. And drop down also some normals. Now let's rearrange this chain, and we want to copy it to create the other shape, the box. So let's rename this one to box. And let's of course create the box. This is too big for now. Let's say 0.1. Delete this other shape. But now we need the points, because with this blast node we are isolating only the splitting points. The problem with the rotation intersection is that we don't have a point there that is always staying still. So to don't end up with shapes that are also moving on the curve, we need to create some other point. So we need to go back inside the solver, and here where we are doing the splitting, at the end of the condition we want to add an else. So if the point doesn't split, so only the change of direction is happening, we want to create a new point. We will call it rot pt, and we will add another point on the current position. And we want to set an attribute on this point, so let's copy one of this line, and the attribute will be called copy, like the one we created for the split. The point is the rot pt, and the value, this time we called split the other one, let's call this other one rotate. And now we close the else. And now we would have a little problem with the add node, because we have more points than the main lines. So on the main chain, before the add, we want to drop down another blast node. And this time we want to delete the rotate point. So at copy is equal to rotate, group type is point, and we want to delete the selected point. For the other shape, we want to use the same blast principle, but use the delete non-selected. So this will carry only the points for the rotation. So let's replace with this blast that we use for the split. And here we should end up with only the rotating point. Yeah, as you can see, there are no box where the split happens. I guess, yeah, no, this is the grid. What's happening here? Oh, that's not a split. Okay, so basically it's working. We can merge also this other one. Let's go forward on the timeline, not too much. And as you can see, we do have the box on the direction change and the octahedron on the splitting. Let's maybe decrease the size a little bit. And for this shape, I actually want to create some overshooting animation. So here in the curve, we want to create something like this. Let's see. And it won't reach the max at the end. Something like this should work. Let's see. Yeah. And as a final touch, I want to rotate only the octahedron over time. So on the point triangle where we define the p-scale, let's also use quaternion to rotate these shapes. So first let's create a vector variable for the normal. We will set it on the z-axis, so 0, 0, 1. And for the angle and the axis, let's say the angle will be equal to the current frame, and the axis is a vector variable. We will set it to the y, so 0, 1, 0. Now we want to update our normal using the qrotate function like before. And we need to rotate the vector, which is the normal, over a quaternion, which we don't have it yet. So let's create the quaternion. Vector 4 quat is equal to quaternion. And as you remember, it needs an angle and an axis. So angle and axis, we created just for that. And now, as you can see, they are rotating way too fast. So let's say frame by 0.02. And it's okay, but they rotate all at the same angle. So maybe randomize it a little bit by adding a random value based on the PT number. So now they are not rotating all from the same angle, at least it seems so. Yeah. So everything together, let's see how it's look. And also let's back and distance these two shape. And we want to also delete this one, it will be lighter. Rearrange, and let's maybe decrease the p-scale a little bit. So let's say between 1 and 3. And also for the box, maybe 1 and 2. So there is a difference. So for my final animation, I just tweak some parameter. I set the rotation chance to 0.1 and the split chance to 0.2. So I ended up with something like this. And you can tweak those values as much as you want, but keep in mind that as you increase the rotation chance, you're increasing indirectly also the splitting chance, so your geometry will increase more. And now for the rendering part, I won't go into a step-by-step workflow this time. This is my original scene, and it's actually super simple. I just created the 3 SOP create node. one for the line, where I gave a p-scale with a relatively low value, is 0.004. And for the other one, it's just a bunch of tries and the geometry inside, so really nothing special. And I believe no special setting here either. Then I merged the geometry and I created a material library. Inside those I have three material. The one for the lines I ended up not using even the color. I just set up some dark value here with a pretty low roughness. For the box and the octahedron I used just some metallic material with the metalness all the way up to 1 and some gold value for the this one is the box and another color for the octahedron. Nothing special here. And then a material linker to assign the correct materials, and the lighting setup are just three very regular light with different colors and intensity. And maybe the only thing I actually set up here was to have a little animation on the depth of field here on the focused instance on the camera. So I ended up with something like this, which is, let me change the background to dark, which is more focused on this part at the beginning of the animation, and then it goes focusing on the nearest part. So that's it for this video. As usual, I hope you enjoyed my content. Like the video and subscribe to the channel if you did. And also thanks for the feedback. They are really helpful for improvement. So have a nice weekend and I hope to see you in the next one.